we will have Raimund Rolfes also online available on new collaborative research center, offshore megastructures, integrated design and operation methodology for offshore megastructures. A lot of megastructures in the title. Raimund, are you online? I see you there.
Yes,
And
I am.
we also see your presentation in full screen mode, so that's perfect. So please take us through your presentation.
I will do so. So thank you very much for giving me the opportunity to report on our new corporate research center, Offshore Megastructures. So this is funded by the Deutsche Forschungsgemeinschaft, which is the German Research Foundation. And this needs an extra word because the DFG is usually very much focused on fundamental research. And it took a while to convince them that there is a lot of room left in wind energy for fundamental research. And it is not only very applied research, which they would not like to fund. So this is a big success where we enter a major research project or open a research collaboration on basic research in wind energy. And yes, it is coordinated by myself at Leibniz University Hanover, which is, of course, also a part of SETWind, the Center of Wind Energy Research in Germany, as Hendrik Heiselmann is also part of. And we have, beside Leibniz University, the University of Oldenburg as partners, the German Aerospace Center, the Technical University of Dresden, and the Free University of Berlin. But the major part is located in Hanover. So what is the motivation? Of course, the motivation behind most of all of our activities is the Green Deal, so the decarbonization of the energy system by 2050 or 2045. And this is a projection here we see on the right-hand side of IAI on the amount of offshore wind energy contributing to the electrical energy. And this will go up to more than 20%. And all of you know about the increase in dimension of the offshore and onshore wind turbines. And we very much think that due to this very much increased demand for offshore wind, these turbines will grow, will continue growing. And we are targeting at turbines above 20 megawatt. And we have four major reasons. A more economically efficient power generation with large turbines, a more continuous feed-in, which I think is very important for the future, due to reduced specific rating, shorter installation times, and more cost-effective logistics and maintenance. And we think that we cannot just continue with upscaling turbines, but we need new approaches. And these new structures will be offshore megastructures, and we define them as slender integral structures of offshore wind turbines with very large dimensions and masses, and they do strongly interact with their environment. If we look into the present design process of offshore wind turbines, we see four disadvantages. First of all, production, installation, operation, and decommissioning are not sufficiently taken into account already in the design phase. Of course, they are thought about, but they are not systematically taken into account in the early design process. Structural monitoring, health monitoring, and adaptive control as well, and nonlinear dynamic interactions as they occur if we have extremely slender, long structures. This might be a design of a rotor blade we could investigate in our CRC with a length of almost 170 meters. So you will have a very strong nonlinear behavior. You will have a breathing of the blade cross-section. You will have also dynamic stall due to the vibrations. And all of this leads to nonlinear dynamic interactions. And also new variable loading and resistance scenarios are insufficiently considered. Consider, for example, a sand dune moving through the wind park over 10 or 20 years. This can significantly change the boundary conditions and influence the dynamics of the structure. So all of this we intend to take into account. Our starting point is that the classical structural design leads to suboptimal structures. One example, very prominent one, is the failure of this type of tripile structures in the park Offshore 1. I don't want to go into any details about this. Now, our objective is now to investigate the physical, conceptual, and methodological foundations enabled by the concept of a digital twin for integrated design and operational methodology. We think that we need an integrated design methodology taking into account a nonlinear and coupled superordinate model. We want to consider all life cycles already when designing, and very important, we want to couple the simulation model and the real structure during operation. And this is done by the concept of a real digital twin, which you found on this slide. The main features of our digital twin are that it is a full coupled model, that it is real-time capable, that it is adaptive and individualized per turbine. So the life of the digital twin begins in the design phase, where we develop new models, couple them, and reduce them in order to have a very fast, real-time capable model. Of course, we have no real structure in that phase. During installation, we will model the installation boundary conditions. During operation, we will add structural health monitoring and control and create a digital representation of the structural behavior. And in decommissioning, we will model the boundary conditions of this decommissioning and integrate it into the digital twin. This is the vision of the digital twin in operation. So once it has been developed in future, how will it work really in operation? We will have a design phase where we have the fast digital twin and detailed design models, and they will work together, of course. You can think about the digital twin as an advanced tool for load analysis. We will do the design and create the real twin using the digital twin. And this will be used in the subsequent life cycle. And then we will measure and post-process data. And they will be used to update the model of the digital twin. And this will enable the digital twin to move from the design phase into the subsequent life cycle phases. And this is what we want to achieve. By that means, we want to have a model of the entire life cycle already in the design. We will be enabled to test new control strategies, to do remaining lifetime predictions, to support condition-based maintenance and plan these maintenance procedures. This is the overall approach. We've broken down this major project into 4 areas: design boundary conditions, design principles, control and monitoring, and the central project is the digital twin. So a very brief look at design boundary conditions. This is everything coming from outside. For example, we develop new wind and turbulence models for the higher layers of the atmosphere. I go back, so we enter the Ekman layer with these large turbines and need to develop new wind and turbulence models. For example, we see here that the probability density function of 3-second wind speed differences is very much underestimated by Gaussian statistics, and this needs to be improved in order to get realistic wind turbine models. Just another example, we need to model the installation boundary conditions, because as I told you already, these can lead to very wrong design decisions. So we will model floating objects for offshore installation, inspection, and maintenance, and will connect this information to the early design process. You see here our large wave basin where we can do some experiments and predict here the movement of these objects offshore. In project area B, we are looking at design principles for the rotor blades, for the support structures, for the soil structure interaction. For example, we look at a holistic integrated design of the support structures, taking into account all life cycle phases, using a database of built structures and of simulated realizations, using machine learning methods for coming up with an integrated holistic design. In project area, this is only one example. You see here are many more projects. I cannot go into the details of all of these projects. In project area C, control and monitoring, we, for example, look at state identification and artificial intelligence in measurement-based SHM. So we intend to develop so-called gray box models, which are a merger from white box, typically physically interpretable condition parameters, and black box models, which, for example, determine residuals of convolutional neural networks, bringing them together with the white box models and ending up in gray box models for improved multivariate structural health monitoring. We also look at robust model update with uncertain inputs. We will start with laboratory structures, then we have data from these large investigations in our tests, in our support structures test center, and of course at the end we will go to the full turbine. In the process of the CRC, the digital twin will be integrated with partial models. Partial models means models from the other sub-projects, for example, for the design boundary conditions. So we will have a complex partial model, for example, a 3D finite element model for the soil structure interaction. The sub-project will develop a reduced partial model that can, at the end, be a simple matrix, stiffness matrix, or it could be a reduced finite element model. This will be integrated into the digital twin and coupled to the overall model in the central project Z01. Yes, of course, and this digital twin creates new loads that will be feedback to the partial models, and which then can deliver new, improved, reduced models. I will skip this. So this is how the overall CRC will work. So at the end, we will have a coupled and reduced overall model. We will work on coupling strategies, efficient numerics, and a robust model update. This is the research infrastructure we are relying on, which is basically located in Hanover. This is the large test center support structures, where we have the big sand pit, the big span, and this is the large wave basin here, and the wave flume, and this is in Oldenburg, the turbulence wind tunnel. Yes, and we are very much looking forward to cooperate with the European Academy on Wind Energy. We will be very present with our CRC on these EAWE PhD seminars starting in Porto this year. And, which is very important, maybe for you, we offer research stays of international researchers, postdocs or professors for 3 to 6 months, fully paid by the CRC in Hanover, to intensify the collaboration. So if you happen to be interested to come for a period to join our CRC, to work with us, please apply to me directly. Yes, and this is the team that started by the beginning of this year. And we are looking forward to a very exciting period. You should know this CRC is initially funded for 4 years and has the very attractive opportunity to be extended for another 8 years. So we might work for 12 years. Thank you very much for your attention.
Thank you, Raimund.
So thank you very much, Raimund, for this interesting talk and this nice prospect of this center, at least for 4 years and maybe even 12 years, also offering a mobility for postdocs and professors. So yeah. I think that's very interesting for our community to understand. In the room, are there questions for Raimund? Yeah, Ignacio?
Yeah, hi, Ignacio Martí from DTU. Raimund, a fantastic initiative. Congratulations. You are putting basic research back into the agenda, let's say, keeping it alive, which is very good news for all. One question it is, how do you work in practice? Is it through PhDs? Or how, if you can elaborate a little bit. And another question is, if we want to have a collaboration with you guys, what would be the way?
So, first of all, yes, we are working with PhD students. So the project is broken down into 16 sub-projects. All of these sub-projects are led by one PI, principal investigator. This PI is usually a professor at the university, right? Most of them in Hanover, some in Oldenburg, some in Dresden, and so on. And the real work, of course, is done by PhD students, yes? This is how we are organized. And we are meeting every 3 months all together for a major meeting. And we have every year a so-called network meeting. And this is where we invite researchers from abroad and from industry to meet with us and to discuss the progress of the research and new ideas. So this year we will have from November 29 to 30 the first network meeting in Hanover, and the overall topic will be digital twins. How do we hear this word very often, and how do different researchers look at digital twins? What is their definition? What is their model behind the digital twin? How do they adapt the digital twin to the real twin? Will be the topic of discussion. And if you are interested to join us for the network meeting, November 29 to 30, please send me an email and we will invite you.
Thank you.
Does it answer your question?
Yes, the question is answered. You can't see it, of course, in the room, but yes,
Okay.
thanks a lot. And we have Arno van Wingerden for the next question.
Yep. Hi, Raimund. Arno van Wingerden here from Hannover IWES. Thanks
Hello,
for
Arno.
Hello. Thanks for a very interesting presentation. I was particularly triggered by your gray box technology because you have, you try to have models kind of explaining what you're doing, and you have these machine learning, something has happened, but I don't know why,
Yes.
kind of approach. So how do you marry the two into a gray box?
I can't say today. This is really very tricky, and I have to rely on my experts concerning this. But there are some very promising approaches, and it will be a challenge. It is exactly what you say. I would like to have some physical explanation of what's going on, and not just have a red lamp going on and saying there's something wrong, but not knowing what caused this lamp to appear.
Okay, thanks very much. I think that's an excellent approach to the digital twin problem.
Yeah, thanks for that, Raimund. And we have a question online from Aiden. The question is that, it's first more or less a remark that offshore megastructures have to be designed to enable lifetime extensions going forward to optimize material use in a future raw material constrained world. And so he pleads for megastructures that have lifetimes of, for example, even 80 years or 3 generations of turbines. Is there something that you could elaborate on here? And you have to limit it to a few minutes.
I will do it. So this is a major motivation for developing the digital twin. We would like to be always in the position to say what is in the actual status the remaining lifetime of our structure, because we have a digital image of our real structure. So we can always say we have now year 20, the designed lifetime, and we have collected all of the loads because we have measured a lot of environmental data. And now we have a digital copy of our structure that exactly knows what is the degradation already that happened. And then we can make a projection what could be the remaining lifetime, taking into account, for example, different control strategies. We say if we run our turbine with a different load control strategy, which reduces loads to a certain extent, we might be able to extend the lifetime by another 5 or 6 or 10 years. And if we repair and our turbine, our blades, for example, we should feed it back into the digital twin, which still is a challenge, and then start with a new analysis. I think I don't want to extend more because it costs your time.
This is indeed a perfect answer, and we see that this is a challenge which needs further research, which is also
Definitely.
sort of a recurring topic of the annual event anyway. So thank you very much. Thank you again.